Hey everyone, I'm Baffled by Reality. Today I want to give a special shout out to the first subscriber and commenter, Dan. Thanks for the support. Now, Dan wants us to take a look at the rim velocity argument. If you haven't heard this term before, keep in mind it's flat Earth speak. Essentially, the argument goes that the Earth's rotational speed is incredibly fast, and we wouldn't be able to stay on the surface if it was really spinning like that, or at least things we observe would behave differently. To give us some further insight on what they're talking about, let's take a look at some Daniel Pratt videos.
Okay, now that we have established rim velocity and what it is for the dummies, well, actually, once again, they're not dummies. They're just lying deceivers, most of them. And then they sucker in lonely people looking for companionship that like to pile on to beat up the little guy. So, how I've stated before, if you are at the North Pole, it will have the slowest rim velocity on the imaginary sphere of Earth. Thus, it will have the greatest gravitational pull. So, if I'm at the North Pole with a test tube of water, it will be being affected by the imaginary force of gravity most at the North Pole and the South Pole. The farther I go out towards the rim or equator, the centrifugal force I just showed you yesterday that shows at 60 miles an hour, people thinking a ball with a rim velocity of 1,000 miles an hour can hold water are insane. I proved it with actual science. Now I say, when you are on the equator, that same test tube of water that you marked the water level up here will be higher. Why? Because centrifugal force, then you would now be facing, so the water would be forced out this way. But if you're standing on the side of the ball, that would mean the water would be rising in your tube. If you're holding the tube up, standing on the side of a ball and your gravity's holding you to the ground, the water level would be going this way, people.
So, Mr. Pratt is in the things we observe would behave differently camp. This is because at the equator, the tangential velocity, what he calls rim velocity, is about 1,650 kilometers an hour. As we move away from the equator to the poles, this decreases until we reach the poles, where the tangential velocity is 0. This is a pretty significant difference. So now we can look at what Mr. Pratt thinks the Earth would look like if it could spin this fast.
So the exciting conclusion. It's like myth hoaxers. I'm going to try to do the destructive bit at the end. Ready? 1, 2, 3. We'll do it slowly. Look! It's an oblate spheroid! It went from a gobstoppers to a Mentos in 2 seconds flat.
Alright, I just showed that part because it's pretty cool to watch. But he claims that his kickball is rotating at 107 miles per hour, which is 1/10 of the Earth's speed. He further claims that rim velocity is independent of radius, which is wildly inaccurate. Angular velocity is independent of radius. So while the Earth is rotating at 1,650 kilometers an hour, its angular velocity is only 15 degrees an hour. This is true for every point on the globe. So when we look at rim velocity, radius is very much important for reasons that involve math. First, let's set up 2 rotating tables of different sizes and set an identical mass on each near the edge. Both tables spin with the same rim velocity and increase until the mass goes flying off. Which mass slides off first? We're looking at the centripetal force equation, where the centripetal force is equal to the mass times the velocity squared over the radius. This is the force necessary to keep the mass moving in that circular motion. So when this force is greater than the static friction force keeping the mass from flying off the table, they're going to go flying off the table. In our example, the mass and velocity is the same for both tables. The only difference is the radius. That means for larger rotating bodies, a smaller force is needed to keep the mass in place. And we can see that as the radius increases, F decreases. As we increase the velocity, the mass on the smaller table will go flying off first. Now, this is something you've probably experienced in real life as well. Imagine being in your car and traveling at 60 miles per hour. This is your velocity. Now imagine going around a turn. You're going to feel your body trying to keep moving in a straight line and exit that curve. The only thing keeping you from doing that is your connection to the car, which might be your seatbelt or the door or just the seat you're sitting in. Then, if you're going around a more shallow curve, you don't feel this as much as if you had gone around a sharp turn. So you are going the same speed, but the radius of the turn plays a significant role. Now let's look back at Earth, where the math gets a little interesting. Most of us accept the force of gravity is keeping us on Earth. Now, if you don't believe in gravity, that's an entirely different discussion. But for understanding basic physics and the heliocentric model, we're going to move forward with it existing. We know that the force of gravity is equal to the gravitational constant multiplied by the first mass, multiplied by the second mass, divided by the radius squared. So if we take this equation and plug it into our centripetal force equation, we get this new exciting equation. Now, this is the mass of the object, and this is also the mass of the object. So we can divide both sides by this mass to eliminate it, and discover that the mass of the object is irrelevant, which is pretty cool. Solve for v, and this is how fast the Earth would need to be spinning to overcome gravity, at least the equator. So this is basically why we don't go flying off into space, why dirt and sand is able to stick to the surface, and why a test tube filled with water will behave the same at the North Pole and the equator. And if you're still not convinced, there are many ways in which we can test that the Earth is rotating. My current favorite is Foucault's pendulum, which goes a little something like this. If you have a pendulum that is able to rotate freely, so it's not fixed to one plane like a pendulum of a grandfather clock, and then you can set this pendulum swinging in a flat plane, which is back and forth with no rotation, the pendulum will over time start to rotate the plane in which it is swinging. And this rotation is directly related to your latitude on the globe. If you're at the equator, there will be zero rotation. Then, as you move through the northern hemisphere, it will start to rotate in a clockwise direction, and it will rotate faster the further north you go. At the North Pole, you should see this pendulum make a full rotation in a 24-hour period. And if you move towards the South Pole from the equator, you will instead see the pendulum rotate in a counterclockwise direction in much the same manner. The flat earthers have yet to attempt to explain how this behavior would work on a flat Earth. So, as we can see, the laws of physics continue to support the heliocentric model, and the rim velocity of our planet isn't nearly great enough to cause any issues. I've been baffled by reality. Stay safe out there.